In this video, we're going to be talking about bond energies. I'm going to also refer to it as bond dissociation enthalpy. And bond dissociation enthalpy is the energy required to break 1 mole of covalent bond in the gaseous phase species. And because the measurements are done in the gaseous phase, this is why it's by definition in the gaseous phase. And in general, a higher bond dissociation enthalpy indicates a higher bond order, therefore a shorter bond length, and therefore greater bond strength. Now, in general, also, energy must be added to break bonds. And if energy is added to break bonds, this was known, and we learned about this before, known as an endothermic process, because our system, in this case, these are the bonds, are going to be broken, so they're absorbing energy. And energy terms that are associated with an endothermic process have, of course, positive signs. Now, when energy is released, this indicates usually that bonds are formed, and this is an exothermic process, which has a negative sign in turn. Now, this leads to how we can calculate, or what formula we will use to calculate the bond dissociation enthalpy. And the bond dissociation enthalpy right here is the sum of the change in enthalpy of the bonds broken minus the sum of the change of enthalpy of the bonds formed. So these are reactants and these are products. Now, note that bond formation releases energy, which is a negative sign because it's an exothermic process, but this has already been accounted for into this particular negative sign, so you do not need to add a negative sign, okay? And double check with Dr. Jensen and I, but I believe you will need to memorize this formula. Now, before we look at the how to calculate the enthalpy change of the reaction, you might also be asked to calculate based on the bond dissociation enthalpy. We're calculating delta H. I forgot to mention that. We're calculating the change in the enthalpy of the reaction. And you will be asked, okay, if this reaction is endothermic or exothermic based on the signs. All right. And if a process has a positive change in enthalpy, this means conceptually that the reactants have stronger bonds than the products. Okay, and if the change of enthalpy is negative, means that it's an exothermic process. This means that the reactants have a weaker bonds than the products. Now let's see, I'm going to walk you through an example of how to calculate the bond dissociation enthalpies. And this is the reaction that is required for us to calculate the bond change enthalpies. And we're going to start by writing the reaction in form of Lewis structures. So I'm going to say here, this is methane plus 2 moles of water plus 4 moles of hydrogen. Okay, I'm going to make room for myself right here. Gas plus carbon dioxide gas. All right. And then I'm going to be determining which bonds are going to be broken. So in this case, I have here from the past example, I have 1, 2, 3, 4 CH bonds to be broken. All right, and then I have 1, 2, but I have 2 moles of water, so 2 times 2, which is 4 OH bonds are broken. Now, on the next slide, we're going to determine how many bonds, determine which bonds are going to be formed. So again, going back to my example, I have here 4 times 1 4 times 1 bond. So I have here, so H2 has only 1 bond, so should be 4 times 1 bonds are formed, and 2 COO bonds are formed. Okay, and in this case, you will be given a table like this table. You do not need to memorize any of this. So do not memorize, okay? And then you will calculate the change in the enthalpy of the reaction using this formula by plugging and chugging. Okay, therefore, I'm going to say that delta H reaction equals to now the sum of the 4 CH bonds plus the 4 OH minus the sum of the enthalpy change. So here's enthalpy change of the 4 HH bonds plus 2 times COO bonds. And in this case, I have 4 times, and these values are going to be given to you on the exam as the number of sig figs 2 plus 4 times 463 minus 4 times 436 plus 2 times 803. And in this case, I get 154 kilojoules per mole. I hope this is straightforward and simple and easy. And let's move on now to a check your understanding problem. And in this particular problem, you are given this reaction of methane and chlorine gas to obtain a product called chloromethane. And we're going to calculate the change of the enthalpy in this particular reaction. And again, I'm going to start by drawing out the Lewis structure of methane plus the chlorine to give me the chloromethane plus HCl. All right, and then I'm going to determine delta H reaction is bonds broken. So the bonds broken, I have here 4 times CH plus 1 times ClCl. Okay, and you see here, the values are given on the slides, minus 3 times CH plus 1 times Cl plus 1 times HCl. Okay, and then I'm going to move on to the next slide to be able to break down these numbers. Therefore, delta H reaction will be 4 times 4, 14, 4D, CH, plus 1 times 243, which is for the ClCl, minus 3 times the 414 again, plus 1 times the CCl, which is right here, the 339, plus 1 times 431, and this should give me negative 113 kilojoules per mole. So I can say that this reaction is exothermic, and the bonds in the reactants are weaker than the bonds in the product. I want you again to work on this problem on your own and try to figure out what is the correct answer. And I'm going to work it through. And we have here an organic, something like an organic structure. Okay. And this should give me, all right, this is gas, and this should give me, now this right here indicates branching shown in the structure. So we can draw it out like this. I have a separate video on how to draw out the Lewis structures of simple organic compounds, so you can reference that. And this is the only product gas. Therefore, delta H reaction is the 6 times CH. Oh, I wrote here CH3, and I should draw it out. 2, 3. So I have here 1, 2, 3, 4, 5, 6. Plus, I have 2 times. So I have one carbon-carbon bond and another 2 times carbon-carbon bonds. And again, the values are given to you. Plus 1 times C double bond O. Okay. Plus 1 times the hydrogen-hydrogen bond, minus, now let's see, in my product, I have 7 CH bonds. So 1, 2, 3, 4, 5, 6, 7. So 7 times CH, right? Plus, we have a carbon-carbon bond. We have 1 and 2. So 1 times carbon-carbon, plus 1 CO bond, 1 times C, single bond O, and then we have 1 OH plus 1 times OH. Okay, and then I'm going to work up here because I'm out of space and I don't think, or I can work on the next slide right here. Therefore, delta H reaction is going to be 6 times, let me just copy and paste the table from here. Okay, so it's going to be, and let me move this down here. So it's going to be 6 times 414 plus 2 times 347 plus 1 times 736 plus 1 times 436. And then this is going to be minus 7 times 414 plus 2 times 347 plus 1 times 360 plus 1 times 464. And this should give me negative 66 kilojoules per mole. And is this reaction endothermic or exothermic? It is exothermic.